Okay, how you doing? We're going to talk about multiplying radicals here very quickly. But before I even talk about multiplying radicals, I first want to talk about simplifying a radical. And one of the things I want to point out to you is that I've got over here bubbled. It's probably one of the most important things you need to know about radicals when you start getting into higher order mathematics, is that it must be left in simplest form, i.e., basically what I'm saying to you is that any factor that is a root of the index must be removed from the radicand, and the root is written as a multiplication outside. Okay? So, what do I mean by that? Let's say I take this and I'm looking at the square root of 72. Sure, it would be nice to just stick the square root of 72 in your calculator, but when you take that and you stick the square root of 72 in your calculator, the problem with it is that you're going to get an irrational number. And for us as mathematicians, we are extremely always concerned with trying to leave things in the most exact form as possible. So actually leaving something as a root is more exact as opposed to actually taking the root. Now for physics or those types of purposes where we start using real world applications, then yes, we take the root of it and we round the value for those purposes. But for us, we are kind of dealing with the exact world where we are like a pure mathematics version and your physics class is more like your applied mathematics course. So for this, okay, there's two methods to this, but let's talk about simplifying a square root. Method one is just writing it as factors, and that's usually what I'm a fan of. I just like to see what is it that what square number goes into 72? Are there any square numbers that are factors of 72? And if so, then that's the one I'm just going to write it as a factor of. So I can take a look at this one in particular and go, okay, what square numbers go into 72? And your square numbers are 1, 4, 9, 16, 25, ... So what I'm going to check here is which one of those go into it. Well, 72 I know is 36 times 2. So I'm going to rewrite this. So this is going to be equivalent to the square root of 36 times 2. Now notice I haven't changed the value underneath the radicand. All I've done essentially here is written it as two factors. And the factors of 72 I have here currently are 36 and 2. Well, the nice thing about this is that 36 is, in fact, a square number. So therefore, what I'm going to do here is that I'm going to take the square root of this. So now, coming over here, what we have is this multiplication property. And this multiplication property states that if you have a radical that has the same index as another, that you can simply multiply those two radicands together. And the reason you can do that actually has to deal with exponential properties, but I'm not going to go there at this point in time. But all we need to know is that this property can be applied. So right now I'm here, and an equal sign means that I can be on either side of this. So I'm here, so what I'm now going to do is take this and write it in its equivalent form on this side. So the equivalent form here is actually the square root of 36 times the square root of 2. Now, for me, I would be skipping this step as you get along and you get more and more used to this. But for now, it's a good idea to kind of write this out until you get in the habit of, okay, the square root of 36. And then we take the root of 36, which is 6, and we say we're going to times that by root 2. And there you have it. There's your final answer. It's in simplest form. And again, any factor that is a root of the index, so therefore square root. So 36 is a square number, so I can pull it out. And I have to do that. When I come down to here, 2, its only factors are 2 and 1. 2 is not a square number, nor is 1. 1 sure is a square number, but it's irrelevant in this because you pull out a 1, then I'm just multiplying by 1, and you don't need to show that. So this is method 1. This is the method I'm going to stick with in this video. If you'd like the different method, I'll make a video of that in a little bit too. So there's that one. Now let's demonstrate this again with a different number. And instead of using an actual number, let's say we have a variable and see what happens there. So I'm going to take a look at what happens if I take the square root of x to the 7th power. And what does that mean? Now, what we need to take a look at down here before I start this problem is there's another property of radicals. And it's very important that you understand and that you review all of your properties of radicals before you try to start these problems, because this is where the bare essential learning begins, and then you figure out how can I apply these properties to what I have. So what I need to be very, very careful of here is that when I take the root out, I'm going to be taking out an absolute value power of it. So that's extremely important. So here we go. So method 1, writing as factors. And that's what I'm going to do. So up here, what I'm going to apply here is this idea that if I have something k, so some root, some index with the same power underneath, then it is just going to be whatever I'm taking this variable to the power of. So what I'm going to do is actually going to rewrite this. Now there's a little index out here that's hidden, and there's always a 2, and that's important to understand just for square roots. It's the only one that will be hidden that will have a 2. You'll never see a 2 there. There is no such thing as the first root that we will be applying. So for this particular one, here we go. So I'm going to rewrite this as the square root of exponential properties. So x to the 7th, how can I create it? Well, I want to create as many of the same indexes as possible. So I have x squared, okay, times x squared, which is now x to the 4th, so I still need 3 more. Well, I can multiply it by another x squared, okay? And then I can simply come up to you and say, okay, well, I also have 1 more x that I have to have in there. And as you get along with this stuff, there are some shortcuts that you'll see, and I'll show you the shortcut in a second for this one. But after a while, what you see here is that I have the square root of x, the square root of x squared, the square root of x squared, square root of x squared, sorry, and then the square root of x. So I'm going to break this apart. So I take the square root of x squared times the square root of x squared times the square root of x squared times the square root of x. And this is where now I can apply this property, where if I have the same index and the same power, then it is just what I'm taking the power of. So same index, same power, this just becomes the absolute value of x. And that's important to understand at this point that I'm working with expressions. Times the absolute value of x times the absolute value of x times, now it's just root x. So what I have here now is, if something is an absolute value, I don't need to worry about if it's a even exponent. But absolute value powers, some things that maybe you should have some prior knowledge of, and if you don't, let's just go ahead and show you some things. That if I have the absolute value of a, and I times it by the absolute value of b, that is the same thing as if I have the absolute value of a times b. Okay, so that property holds true for absolute values. So coming over here, I'm just going to multiply all these together. So what I have is the absolute value of x cubed times the square root of x. If this were an even exponent, I would not need to worry because whatever I plug in for x would automatically become positive. But in this case, because it's an odd exponent, I must leave the absolute value symbols around it. So I said I'd show you a shortcut to this. Well, very simple. The shortcut here is, how many times does 2 go into 7? Well, 2 goes into 7 3 times. So we take out 3, okay, 3 powers, so x to the 3rd power. What's the remainder left? Well, it's 1, so we can get right to this very quickly as we learn the shortcut from here to here. I just wanted to show you a demonstration of it, so I hope you understand what I meant by that. Again, how many times does 2 go into 7? 3. How many times? What's the remainder of 7 divided by 2? The remainder is 1, and that's how many x's get left on the inside. So I have 3 x's on the outside being multiplied together, and I have 1 being left inside. So that's kind of the shortcut. Alright, so that's kind of your bare basic bones of simplifying, so let's get into this idea of multiplying. So a couple things I'm going to multiply here. I'm going to take the square root of 6, and I'm going to multiply it by the square root of 15. So again, I'm going to utilize this property here, which the multiplication property says to me that I can come up here and multiply these two on the inside. However, what I want you to understand is that you can multiply them, but that will make a bigger number, and then you have to figure out from that bigger number what are some square numbers that can go into them. So what I like to do is actually rewrite these very quickly as factors, okay? And I look for a common factor, and that's how I'm going to write it. So in this case, 3 is a common factor between 6 and 15, so I'm going to make sure that I have a common factor of 3. So I times it, and what I've got here is 3 times 5, okay? And then I put them all together. Remember, a number multiplied by itself is a square number. So now let's say I put them all together. So what I have here is the square root of 9 times 2 times 5. And then I utilize this property over here. And over here, see there's two numbers. Not a big deal. I could have 3 and I could utilize the same property on both sides. But what I'm left here is that I have the square root of 9. So now I'm going to do a little shortcut like I said I would before. Square root of 9 is 3. So I pull that out, leave it as a multiple of. Well, 2 times 10. Well, I mean 2 times 5 is 10. And we leave it as that multiplication of 2 times 5 being 10. We don't leave this as 2 times 5. What you just need to note is that there are no square numbers that can go into 10, so we actually leave this as the square root of 10. And the final answer to this one is 3 root 10. So 3 times root 10 is the final answer to that one. So I hope you see what happened there. Let's do another one. So here we go. So we have the square root of 8 times the square root of 10. And again, like I said, I like to try to factor it into the point where I have square numbers. So if I have these two, okay, I'm always looking for what is a identical factor that will both go into 8 and go into 10. And the identical factor that I can think of at this moment is 2. So I'm going to write this as a factor of 2. So here we go. So I get 2 times 4 times 2 times 5. Okay? So then we go on with this. So now I continue on, and what I'm left with here is the nice thing, okay, is that I put them all under one roof, and when I put them all under one roof, I'm going to do this 2 times this 2, okay, which is going to be 4, times it by 4, times it by 5, okay? And now what I see here is that this right here will produce a square number, and that square number will produce a 16, okay? Or I could rewrite this simply as 4 times 4 is really 4 squared, right? And then what I have here is that I can utilize this property. Now that the same index, same power, that this is just going to be a 4 on the outside. So 4, now root 5. Now, it's not necessary to put the absolute value of it. What this is just saying is that you would take the absolute value of that number. So, the absolute value of 4 is 4. That's why I don't write it unless it's a variable, because a variable you don't know what you're plugging in. But if you were to say it was to plug a negative in, and then you had left a variable underneath, remember you can't take the square root of a negative. So this answer is 4 root 5. So that's the final answer to this one. So on to another one. Okay. So how can I bump up these problems? Well, I can introduce some things with distributive property. And you're not doing anything different. What I just demonstrated was this multiplication property of the square root of a times square root of b equals the whole square root of a times b. So let's say I bump this up and I put some distributive property capabilities into it. And I look at, okay, I have the square root of 3 and I'm multiplying it by the quantity of 4 plus root 5. Okay, so now I have this quantity. And all I want to do is just multiply it through and then simplify if I can. So I take root 3 and I multiply it by 4. Well, root 3 times 4 is going to be 4 root 3. And what I want you to understand here is that I don't do 3 times 4 because this has a root, this also has the root. So this doesn't have a root that I'm taking of it, so I can't multiply the 3 and the 4 together, and that's important to understand. But what I can do is I can think of this as like an x times a y. And what's x times y? Well, it's xy. So in this case, I'm going to think of that, in my head, I'm going to think as like xy. So what would you get x times y is xy. So this is going to be 4 root 3. So I hope you understand what I mean by that. Let me write that a little bit cleaner. Okay, so we get 4 root 3. Then I add to that. Now, in this case, now I can do this 3 times this 5 because now it demonstrates this multiplication property over here where it has a root times a root. The indexes are the same, so I can multiply what's underneath. So I can do 3 times 5, which is 15. So this becomes root 15. And at this point, what I want to check for is there any square number that can go in the 15. So the only square numbers that are below 15 are that I'm concerned with. 1, we kind of throw out the hatch. We don't really need it. We're really only concerned with 4 and 9. 15 is not divisible by 4, nor is 15 divisible by 9, so square root of 15 is in its simplest form. 3, again, simplest form. So what I have here for this one, in fact, is the actual answer, is 4 times root 3 plus root 15. You can't add these two, and that's an addition property of your roots, and I'll talk about that in another video. So this is the final answer. Not necessarily maybe simpler looking to you, but we're just talking about utilizing the multiplication property. So here we go. Continuing on, let's do another. So let's say I have this now. So this will be my final example in this video, but let's say I have 2 root 5, and I'm going to distribute that amongst the quantity of root 10, okay, plus 3 root 3. So this is my multiplication property that I'm going to deal with. Now, what I'm going to do here is I'm going to take a look at this, and these are the things I'm multiplying together. The number that's in front of 10, we can think of as like coefficient-wise as being a 1. So what I'm going to do here is much like you had in algebra, like you had 2x times 3x, and you would get 6x squared, you do the same thing with roots. They hold that same sort of property. So 2 times 1 is 2. Now we look at root 5 times root 10. And again, I'm going to start to look at what are the common factors that 5 and 10 have. Well, 5 can be divided by 5, and 10 can be divided by 5. So right there, I know that I'm going to be able to pull another 5 out, because this has a factor of 5, and 5 and 5 makes 25, so the square root of 25 is 5. Okay? So I'm keeping track of this in my head, and if you want me to write it down, I'm more than happy to do so, but so let me write that down. So I have this, and I'm going to write 10, okay, as being broken to its factors. So this is really, okay, 5 times 2. So here's my root 5 right here, and here's my root 10. So what I have here is 5 times 5, which is really 5 squared. Utilizing this property out here, I pull out the 5. So what I'm left with is 2 times 5. So this 2 times 5 times root 2. Okay? So again, I'll write that step up here that I did. And this is kind of things that I'm starting to do in my head, and that's because I've had lots of practice with it, but I would suggest maybe writing this little baby step out up here. So that now I have this 2 times 5. So this right here becomes 10 root 2. And after a while, you'll understand what this is happening after you do them like this. I don't suggest skipping this until you get in the habit of really being able to do it. Where I'm at currently is that I can go from this multiplication right here, and I'll be able to go right to that answer. But that's because I've had years of experience with this. So I only suggest that you do this until you get to the point where you're comfortable that you can go from here to here. And if you can do that right away, awesome. But my last step here is distributive property, which means I must distribute this over here. So I get adding, okay? 5 and 3 share no common factors, so I'm not worried about breaking it apart like this one. So now I'm just going to go ahead and do it. So 2 times 3 is 6. And then root 5 times root 3, so applying this multiplication property again, just gives me root 15. And now there's nothing more left that I can do. I can't break 15 into a root of 2. If I could, that would be great, but I can't in this particular case, so I can't add these two roots together. I'm just left with the idea of this being a root 2 and this being a root 15. And then that's my final answer. So I hope that helped with multiplication of roots and simplifying roots, and I'll be putting another video up of what happens if I have two quantities multiplying each other. So I hope that helps.